Welcome, civil and structural engineers. In this training webinar, we will learn about the structural analysis and design software STAAD. It was invented in year 1978. At that time, it was called STAAD 3 and it was a text base. So where engineers will provide input in a text file. Then it moved to a powerful graphical user interface where it was called Structural Analysis and Design Pro. And now we call Connect Client where the key, the software license is on a cloud. In olden days, the memory, computer memory was a big asset. So the STAAD, there were 4 options which is still available. So when we say space, STAAD space, each joint will have 6 degrees of freedom, 3 translation and 3 rotation. But if I just want to perform a continuous beam analysis, which is a 2D analysis, a continuous beam, so I can inform STAAD plane. So plane, it has 2 translation degree of freedom, which is a translation in X, Y, and rotation above Z. So when the 2D drafting softwares came into picture, they had X, Y plane, and we will put points line in a XY plane. So STAAD also started with Y up. So the gravity direction in STAAD is minus Y default. And when we say truss, so each joint, it will have only translation degree of freedom. So the members will take push or pull. That is about truss. So plane, we can take bending and shear. And in space, 3 translation, 3 rotation. So each member at ends, it will be having 6 forces, Fx, Fy, Fz, Mx, My, Mz. And if you want to do a grillage or a floor analysis, which is in XZ plane, so we can write STAAD floor. So when we do this, it remembers like each joint, he has to allot how much size or what will be the one member matrix size. So when we run STAAD, we create a geometry, we assign property to the line or beam members. Then we give some specification like we want to release, offset. So they are called specification. Geometry, property. In property, we give cross section and beta angle, like how the member will be oriented. That we call beta angle specification. Then we give loads, boundary condition, meaning supports, and then instruct a load combination, and then we tell the computer STAAD perform analysis. And then comes a design part. So this all thing perform analysis, they are called preprocessor or modeling. And then we go to post processing where we verify the results from STAAD. So the first step of geometry is creating joints. So in some software they call joint, node, or a point. All is same. So instead we give instruction and x coordinate, y coordinate, and z coordinate. But here in a one line we have start joint, end joint, and start node coordinates xi, yi, zi, and last coordinate. So what he will do, he will interpolate at equal distance the joint. So here I have 0 x and x equals to 10. So if this is 0 comma 0 comma 0 and 10 comma 0 comma 0, which is node 11, we will get in between 2, 3, 4 up to 10 equally spaced nodes. So by giving such a single line, we created 11 joints. No need to give coordinate for internal 2 to 10 joints. So if I want to replicate this 10 times, so we write repeat 10 times and then give delta x, delta y, delta z in that direction. So he will again repeat this 1 to 11 10 number of times. And if we want to repeat complete block, then we say repeat all. How many times? In delta x, delta y, delta z. So by writing just 3 lines, we can create a 3D structure in a space. So if we stop up to this, it will be 2D, and repeat all, it will create a 3D. So let's remember, we can create joint coordinate line by line. So I can just go on writing x1 0 comma 0 comma 0 2 at a 5 meter distance. Like this also I can do, or I can write a single line like 1 is 0 0 0 and 4 is 15 0 0. He will interpolate it equal distance node 2 and 3. And another capability, we can import drawing exchange format into the STAAD. These are 3 different file format which we can import. So once we created joint, so when we join 2 joints, we get member or a beam, a line. So now we write like each entity in a STAAD, it has its name. So node name 1, 2, 3, their name. So same way member, it has a name 1, 2, 3. So member ID, which someone will call member ID, start node ID, end node ID. So and we can create multiple members. So there is option. If I have like this in a series, node 1, 2, 3, 4, 5, and I want to, I will put in a circle. So node ID I have written this way. Let me use another color for member ID. So member I am writing by this color 1, 2, 3, 4. So I have to create 4 members. So by single line I can do member 1 is between 1 and 2. Do this up to and last member, which is 4. So when you are doing, the member number is increasing by 1. So this is member increasing ID, and the node, say the first member was between 1 and 2, next member is between 2 and 3. So the joint is getting jumped by 1. So this is joint jump, member jump, last member, and start node, end node. So by putting a single line, we can create multiple members. And if you write repeat, so it will create in another direction. And one more repeat all, it will create a 3D. So this was about line element, line member. If I want to create a triangle cell element, we write member ID, element ID, and then the 3 nodes. So here, like we have created a 4 noded element I, J, K, L. I, J, K, L. So you can move anti-clockwise, clockwise. Based on that, the third axis of the plate will get decided. So the plate local x-axis will be between I and j, and the local y-axis, it will be from j to k direction, and it will use right hand rule to find the third axis of the element. And if we want to, we have three options: cylindrical coordinate system, also spherical coordinate system, also in the STAAD. So we learn about joints, member and element, and automatic multiple generation. As we said before, the modeling, it has 4 steps: geometry, general analysis and design. So we learned about joint coordinate, member incidences, element incidences. Now we have to give property. So if it is a plate, the thickness of the plate, then spec, like if I want to give release, offset, so they all come under spec. Truss member, tension only member, compression only member, they all come under spec. Then support, like a pin support, fixed support, fixed butt. So if we want to release some degrees of freedom, we call fixed butt. Then loads and load combination, material. So now let's move to the next slide, and we can give commands for post processing, like print for me joint displacement, support reaction. So all the instructions which you give to STAAD, it will give in a output file. So this is a typical 2D interface. We can tell the software, okay, can you create a grid line for me, and grid plane, so we can snap our joints to the grid intersections. So we can create grid lines for creating geometry, and we touched on this topic at the beginning. Node ID, coordinates x, y, z, and instead if you want to write multiple joints in the line, so we separate by this symbol. And there are options: add beam between node to node, midpoint to midpoint. So they will come under geometry. And in like all normal software like Word, Excel, we have a copy paste command. So here also we can copy paste, Control C, Control V. And if I want to create a multiple copy, so which we call translation repeat or array circular repeat. Suppose so I'm drawing a plan and I want to make circular shape this column I want to copy. So I will give like this command. So it will make circular array for me. And then there are simple commands like split, join, intersect, extend. So if I want to split a beam into two parts, like I want to add at the midpoint. So I will say add midpoint. So how many joints to be created? So he will add. We will understand concept of local axis here. So when we join I node with j, that axis is called x-axis and it is blue color instead. So now we remain with the two axes, local y and local z. So as we know, in a STAAD, x and y is up. So now local x is defined. So local y is always along global y. So this is the first principle. Local y is always along global y. So all beam, the beam elements their local Y is along global Y and it is red color. So now using right hand rule, moving from X to Y, your right hand finger, we get the third axis, which is Z axis. Now you will be curious if you have a column, uh, like we join column vertically. So the local X is along global Y, X is defined. So now we remain with two axes, which we have to define Y and Z. So what happens here in a case of a column, since in STAAD plan we have X and Z axis. So for column, local Z is along global Z. Local Z is along global Z, and then we can find out the local Y axis. So if you want to define steel, it has a library of all international shapes: European, American, Australian, Korean, Indian, all cross Chinese cross sections are available. Again, we can pick a different profile like I, H. In British, it is called UC and UB. And in case of European, it is called IPE and HE profiles, H profiles. So we have complete library, and you can make built up also. Like if you have a plate and you want, H profile, you want to add plates top and bottom, we can use different thicknesses. We can define a section which is T, which is made from H profile. Like we have a H profile and I cut at the center, so I will get we will get two T's. So that is called T cut from UC or UB or HE I. So T cut is also available. And if you want to just define a rectangular, we can give YD and ZD dimensions. And if it's a circle, we require only diameter YD. So this is all about local axis instead. So let me revise. We have three color: local X, local Y, local Z. And local X is simple. It is the axis connecting I node to the start node to the end node. So here the demonstration of column. So column start and end. So that becomes local X. And we had a global X and global Z. So local Z is always aligned with global Z. So now if you want to place a column which is like this, we will give local beta angle. So that is beta angle we can specify. So in case of a beam, this is a stronger. So this is we call y-axis, and sorry, beam, we have this y and this one z, because y-axis is along a global y. So that's why for beam, like when we do 2D analysis, we check mz moment. So this was about local axis and global axis. Similarly, for plate also we can find local plate axis. Steel sections, like we can assign property steel sections, prismatic, and they have a built up section builder also. So if I want to make a column using 4 angles, that is also possible. See, channel back to back, front to front. So all these different options are available, and we can make our built up section also. Specification, as we mentioned, we can give release at the beginning and at the end. Like whenever we make a steel connection, we have a two type of connection: simple connection and moment connection. So if we want to release moment at the start and end, we can use specification. So that is called release command. Or truss member, tension only member, compression only member. So all this options are available in specification. Then comes loads and load combinations. So we can define our loads, different load cases, 1, 2, 3, and it has inbuilt wind and seismic load to all the international standard. So in seismic, again, we can do both equivalent static analysis and response spectrum analysis, and it has a capability of performing time history analysis, also linear time history analysis. And if we want to material, we require E value, Poisson's ratio, density. So once we specify density and cross section, we can calculate self weight. And what more, like sometimes we want to give massless element, so we can give density close to 0. So when you apply self weight, that as density 0, no load will be applied. So this was about spec. So in spec, one more feature is that for RCC building with slab, it what slab does function, it provides in plane rigidity. So all the nodes on this slab, they will move together in x direction, and they will move along z direction, which we call in other software diaphragm, rigid floor diaphragm. So instead, it is called master slave. So these are called constraint. We have two aspects in a software structure analysis. We call restraint, which is a boundary condition, supports like fixed supports, roller support, pin support. And in case of a constraint, it means the displacement relationship between different nodes. So any one node on a floor we call a master, and remaining as a slave. So slave, they will follow the master. And we have option slaved in a XZ plane, as we have seen, like in a, if we are modeling a 3D building, XZ becomes a floor plan. So we can directly say uh, slave direction ZX. Or you can capture this also, like Fx and Fz displacement is same, and rotation about Y. So if you don't click this, you can click 1, 2, and 3. And if you want all the 6 degrees of freedom uh, rigidly connected, like two joints I have, and I want to say they will move together, they are connected with very rigid element. So we can say rigid body motion. So that is about spec. And support, it has default options like fixed, 3 translation, 3 rotation. Fixed means it will be 0. Pinned, 3 translation 0. Fixed but, so if you want to release some degree of freedom, then we go for fixed but. Enforced we use when we want to give some displacement, like if I have a continuous bridge and one of the support settles during service, and we want to find out its action with the bending moment and shear force, at that time we use enforced but enforced. These two options are for support settlements and support rotation. And it has option of giving support which is inclined. So when we say inclined, we have to define, we have to give local this axis. So it will make support in that direction. So inclined is also option. So inclined we sometimes use for natural draft cooling towers, where we want to place our support like this for column. So that is inclined. And tension compression on the spring. So if you want a soil which cannot take tension in vertical direction, so that time we use compression only spring. So this was about support, and we can give fixed, but means I can give spring value in any direction, 3 translation and 3 rotation. So KFY, KFX, KFZ, they are translation spring and rotational spring. And here comes now the load definition. So first we create different load case names, and STAAD, it has a one more capability they call reference load. So reference load is we define at the beginning, and for that it will not solve the matrix. So like what it is using stiffness method. So in stiffness method, the software will make all degrees of freedom first fix, and then it will try to solve. So that's what we call stiffness metric. Kx equals to F. And there, like we are finding displacements. So reference load, when we declare at the beginning, he will not solve for that load case, but in the main load case, we can call that reference loads. So they are defined like R1, R2, R3. The reference load command is also very useful for seismic mass declaration. It has a repeat load command also. So repeat load command, we want to combine different loads uh, for performing nonlinear analysis or large displacement analysis, tension only, compression and only members. So we go for there is that like a repeat load and load combination. They are different. So in load combination, what happens if you have load 1, 2, 3, and you run the analysis and you give command load combination 10 is 1, 1.0, 2, 1.0, 3, 1.0. It means the load combination 10, it is load 1 is 1 time. This is the factor, load factor. So first is load ID. 1 is a load ID, and factor like by how much it has to be multiplied. Like in like American standard, we have 1.2 dead load plus 1.6 live load, or in European 1.35 dead load plus 1.5 live load. So the load factors. So in repeat load, we give it becomes a primary load case only. Load 10, then repeat load command, load 1, 1.0, 2, 1.0, 3, 1.0. So he will do matrix analysis for this will become a primary load case. It is not doing like in case of a combination, we are just adding the output results. So in this combination, if we have a truss member, so the tension or compression force in a member, he will like load case 1 he has solved. So he found some force F1. In load case 2, he found F2, F3. So he will just give mathematical addition F1 plus F2 plus F3. But in case of repeat load, so in that structure, he will apply load 1, load 2, and like whatever load 3 we have defined. So this becomes primary load case, and he is analyzing and he is calculating forces for us. He is not just doing the output results addition, like mathematical addition. So these are some primary load cases commands. We can apply joint loads, member loads. So in case of a member, again we can go for like a joint load, a point load uniformly distributed throughout the length. We can give trapezoidal load. We can give partial uniformly distributed load. So these are all possible option. Triangular load case and element load, earthquake load. So for joint load, we as we said, we can like if it is enforced or enforced, but we can give support displacement. And 3 Fx, Fy, Fz force, and 3 moments at any given joint we can apply for a space structure joint load. So this is joint ID, and then in fx direction, fy direction, fz direction, mx, my, mz direction. So here I can put multiple joint ID. If we want to apply same, then we can give list. And instead, if you want to continue to the next line, then suppose here fx10, if I'm continuing on the next line, I can just put a dash line and move ahead. So this is a character. Dash is a character for multiple, like if you want to write command for multiple line. And there is a one more feature available, grouping. We can create a group of joints, members. So what is the benefit of creating a group? We can assign forces to a group. So when we assign here, it becomes like this. Floor 1, that is a group, and then you are applying force. So you can give any group name. Like we have a joint ID, member ID, so group ID. So this slide shows us all possible options of applying a load on a member, the beam or a line. Uniformly distributed load, and then direction. We can apply in local direction, global direction, and projected. Projected means if I have a inclined beam and I just want to apply a load like this, so it becomes projected. But if I have a roof, portal frame, the load acts, if parallel to ridge, we can apply along local axis. So like we can apply local, global, and projected. And then ID, uniform GY, the load value. D1 means the start distance of uniformly distributed. D2 is a and where it is stopping. So it will apply for the length of D2 minus D1. And if we have eccentric this load, then the D3 distance. Eccentric means if this is a neutral axis, x-axis, and like it is offset, then we can give D3 distance. So uniform load, uniform moment, concentrated load. So again, concentrated load we can apply along local and global. Value, distance, and then D2 is eccentricity. Since it's a concentrated load, we don't have to give start and end, and you can give multiple lines. So on one beam, I will apply multiple concentrated load. So for each load, we will be having one line. Concentrated moment, linear. So linear, it will apply for the full length. That is the difference between uni and linear. So in uni, we give starting distance D1 and end where it is stopping D2. But in uni, we don't have to give the distance D1, D2. We have to tell like what is the load at the beginning and what is load at the end, W1, W2, and along which direction. Linear. So we are writing linear. So it is always along local. That is the difference between linear and uni. So linear load is always along local axis. Start and end. So if you want to apply a load which is a triangular, then you just keep this to W1, W2 0 and specify the value W3. Trapezoidal at the beginning, at the end, D1 distance and D2 distance. And we can specify prestress also. So we have to specify eccentricity at the start, mid, and end. So let us make summary. We can apply uniform load, uniform moment, concentrated load, concentrated moment, linear, trapezoidal, and prestress. So now we come to plate element, or like we call cell element. Yeah, cell. So the cell it gives us totally 5 plus 3, 8 forces. So the forces which are acting in a plane, these are called in-plane forces. They are in-plane stresses. So they are three numbers: sigma x, sigma y, and shear. And out of plane, it means like moment we saw by two arrow together. So again using right hand rule, we move in right hand direction. So this is myx moment, my moment. So this moment will create tension at top. And at the beginning we saw what is the local x-axis. It is joining I and j. So that is a local x-axis and local y-axis. And the third axis, which is z, it is getting decided by moving our fingers, right hand fingers, from x to y. So cell element, it will give us result total 8 forces in plane and out of plane, and it will give us stresses also, sigma y divided by thickness. So stress in this direction. In another software like SAP 2000, they have 112233. They use, instead of XYZ, 112233. So when we have a membrane element, we get only these three forces, and cell element we get 3 plus 5, 8. So this is the last slide. What other things are available? It has a now a space bar key. So once you press a space bar key, it is like a gene, uh, chirag. So you touch the chirag and gene will come. How I can support you? Same way you press a space bar key, and then it will pop up with the option. You can select nodes, beams, plate, solid, geometry. There is a sometimes to apply some loads or give property, we want to select particular beams. So it has option like select beams parallel to global XYZ. We can select by property name, and before running the STAAD we say by missing property. And one more thing in a STAAD, like if you forget where is that uh, option, so on top you just type, okay, please share uh, node to node distance, that it will show where that command is available. So always use top this menu. It will be like question, you type here and you will get answer. We can select by IDs, group names, uh, in a plane, particular plane, by material. So these are different options available to select beam, joints, or element. There is a in utilities option to calculate distance between nodes, and once you want to remove all the distances, you there is also option again to remove all the distances. And in a text file, since you are creating a file, you want to communicate your thoughts with other, so you can just put star and write, so that becomes comment. The STAAD will not read this line. And continuing line, we show a hyphen, so it will continuously start reading. And the tool which is available in STAAD to create a built-up section, it is called section builder. And we can perform in analysis static check, like what was my total action and total reaction. So the total reaction, it will give again some fx, fy, fz, mx, my, mz. So using this, we can find where the action is and where the reaction. So equilibrium check. So let us summarize what we learned today. The STAAD we create in 4